Okay, we are going to complete related rates as far as in-class instruction probably today. That is our goal. You've got a project due in lieu of a test over related rates, okay? I emailed this to you last night, related rates project. We'll talk about it a little bit and answer any questions. You can work in groups if you choose to, no more than 3 in a group, okay? If Josh and Hamilton and Jamie decide to work together as a group and they let Jamie do all of the work, number 1, they can't complain because they made a good or bad grade, and number 2, Jamie can't complain because they didn't do any work. If you don't like the person that you're working with, don't work with them, okay? I'm not going to play petty elementary grade games with you there. Do the work. I expect you to load the work accordingly to everybody do some work there. You have to make up a related rate problem, okay? Don't Google related rates. Find the problem and write it down, because if you can Google the problem, so can I, all right? So don't do anything that obvious with what you're doing here. You've got to illustrate the problem. Now, you don't have to go overboard with that, but do some illustration. Don't just write the problem. If you've got 2 cars, one going in town and one going out of town, be sure you've got something that resembles cars there, not just the word car like I would do. If you've got a scene with somebody walking towards a lamppost, be sure you've got that there, okay? Now, when I say make up a problem, I'm not saying part of it cannot be there at all. Okay, let me see if I can clarify that. We've worked a problem on a car going out of town and a car going out of town and a car going in town. That doesn't mean you can't do that problem, okay? You can do a problem like that. I don't want you to do that problem with the same numbers that we worked in class, at the same points that we worked in class, or the same thing as what you can find off the internet. So it can be the same type of problem like that. You know, we have worked x squared, y squared, z squared. We did that with the airplane the other day. You can do something like that, just don't use the same numbers as what we've used before. It should be something that's unique to you in that respect, okay? You must work out the problem, label drawing, have your formulas there. Don't just write down the answer. Some of you like to do that. That's not good enough. Show the work, show the steps that can go there. If it needs any explanation, explain it, okay? I can't tell you if it needs explanation or not. Be sure the problem is in the box that you're going to be turned in. Be sure that your answer has a formula, complete solutions, and neatly covered box with your names on the box. This is the rubric that I will be using to grade this with. Difficulty level, I expect you to have some questions about what do you mean by difficulty level? Funny you should ask. This is what I mean by difficulty level. These are what I consider easy problems. These are what I would consider the more challenging problems. So if you draw a circle, if you drop a pebble into a pond and the ripples go out from there, don't expect to be graded high on difficulty level, okay? Because that's not a difficult problem. If you do something down here where you've got the volume of something and it's getting taller or shorter and wider or narrower at the same time, and these two are moving independently of one another, that's a more challenging problem there, okay? So expect to get more points there because there's more places for you to make a mistake at that level down there. So look, that's something, if you want that, you might want to take a picture of that so you'll have some idea of what type of problems you're looking for there, okay? Any questions about this project? It's due next Wednesday at the end of help class, which is 1:30 next Wednesday, okay? We will not have time in class to work on it. You will have help time on Wednesday if you don't go to the softball game, that you could work on some of it then. If you do go to the softball game, obviously you will not have that help time to work on it. Yes, ma'am? Softball on Wednesday, you check out at 1:50. This class starts at 1:28, so you'll be here for about 20 minutes on Wednesday. How many of you plan on going to softball? Personally, if I were you, I'd go to softball, but that's up to you. I mean, if most of you want to go to the softball game, I'm not going to take up anything new. Here's what I'm saying on Wednesday, okay? It's important to go support your team there. So it's okay with you to go do that. So really, if you don't go, since we've only got 20 minutes, I'd say worst case scenario is we may work one FRQ on Wednesday or something like that, something relatively simple. Tomorrow we're going to start on a new topic. I'll open that up and email out what that topic's going to be for you later today, I guess. Any questions on your project? On your project. Where do we find the root part of this? This was emailed to you in an email last night. Also, if you go on to Moodle and you see something there that says Related Rates Project, if you click on it, it should be attached to it there also. And if you can't find it in one of those places, email me and I'll send it back to you via email. Okay? So you've got that to be working on. You have a web assigned due Wednesday night. Wednesday night you have a web assigned due, okay? It's on Moodle. It should be on RenWeb. But Wednesday night you have a web assigned. Today we're going to finish up working a few more examples in 25. So you should go ahead and open that up. That's the last one we were working on the last time we met. Today we're going to work on a couple of more challenging problems, at least challenging for us to look at. We're on about slide 4 or 5. It looks like we're in a swimming pool. We're thinking warm summer thoughts, swimming pool. Okay. Read over that problem and write down what you think you know, what you think we're looking for, and then we'll go on through it. You don't have to go ahead and finish it off. I want to see what you can come up with on your own, and then we'll go forward from there. I'm really not worried about A part. We're not even going to look at it, so that question is beneath us. several people have that written down. What are we looking for since we're doing B part? Rate of water level rising. So what kind of letter do you want to use for that? R? Is that what you said? Y? R, Y. So, okay, let's use dr over dt. That's what we're looking for the rate that the water level is rising. Some of you might choose to use H for dH dt for how high the water is at a particular time. So we know obviously we've got 12 meters long, 6 meters wide, 1 meter deep at the shallow end, 3 meters deep at the deep end. All of that sounds confusing to begin with here. What relationship, what are we looking for? What's our relationship that we've got going on here? We need a volume. Well, how do we find the volume of this pool? Anybody remember? Okay, I'm going to take this front piece right here and redraw it. It's kind of made larger here. But that's what a cross-section of this would look like. Okay? So if we're down in the ground, we can look and we could see the side of the pool looks like that. So how tall is this? 3. And how about this? 1. How about from here to here? 12. Okay. And this is a straight line we're going to assume here. So how do we find the volume? Well, that's just a one-dimension thing. I mean, 2 dimensions, length and width. Volume, we need a third dimension to it. What's our third dimension? 6, okay? So we know that this pool goes back in there a distance of 6. So how do we find the volume of something like this, though? Yes, sir, Jerry.
Use 1 plus 3 times 12 over 2 and all times 6.
Said 1 plus 3 times 12 divided by 2 times 6. Is that what you said?
Yeah.
Okay. Why did you say use that?
Because that's the area for the shape like that.
Anybody remember what this shape is called? Truncated triangle, almost. It's called a trapezoid. Okay, the area of a trapezoid is B1 plus B2, these two parallel sides, times the height, the distance between them, 12 divided by 2. Okay? Huh? B1 here plus B2 here times the height here divided by 2. Because if you look at it, if we were to take this and draw a diagonal in here, we've got 2 triangles. We've got a triangle up here, base times height divided by 2, a triangle here, base times height divided by 2, and the height, or one of them is the same on both of them. Okay, that's going to give me the volume. Well, I don't have any variables in there, so this pool's not getting any bigger? So the water's not going up in this pool? The size of the pool's not changing. This tells me the size of the pool. So the size of the pool is 224 times, it's a big old pool, 144 cubic meters, something like that, I think. So how can we, so what variables do we get to put in there now? Because this is the size of the pool right here. We aren't concerned with, we need a volume formula that has some letters in it, that has some variables, specifically that has the radius in it. So which of these numbers, 1, 3, or 12, is the radius is this R going to be associated with? 3. So this is going to be an R. That's going to be changing there, okay? So what else is changing in the pool? Is the 6 changing? No, the 6 is not going to be changing. So we know we're going to have a 6 in our answer, in our problem out here. We know we're going to have an R in our problem. Well, the 12 is changing. How is this thing here changing? We're not up to that point yet. We're just moving up right down here. So the water level is somewhere in here. So this would be our R, and this would be, well, I don't want to know if we want to use H or not. What do we want to use for that? B, kind of like our base. So we've got an R times a B, or we got an R and a B. How are we going to take into account this, bless you, how are we going to take into account this little rectangle up here? Length times width times height. Is the water up here? So does it really matter? Not yet. So, and when are we talking about? We're talking about when there is 1 meter of water at the deep end. So there's 1 meter. So we're at about this level right here. Would you agree with that? So we don't need to worry about this top rectangle here. It's as if, right now, it's as if that's not even there for us, okay? So we just need R, B, and how deep. Now, do you think our volume is going to be R times B times 6? Why not? Why do you think it's not going to be R times B times 6? It's a triangle. This, wouldn't you agree that this shape right here is a triangle? So how do we find the area of a triangle? Base times height divided by 2. And then this gives us the area of the triangle times the height or the width of the whole thing. I don't think y'all have ever seen this before. Have y'all ever seen that? V equals capital B times H. To find the volume of anything, you're trying to find the area of the base, which is this end down here, times the height. Think of this as a single triangle, and to make the pool, you're just putting a bunch of triangles together. So you need to know how many of them. You're putting 6 meters worth of them, and you need the area of each one. If you add all of that up, that gives you the volume of it right there. So the volume formula is the volume of is the area of the base times the height, which is R times B divided by 2 times 6. How could we simplify this? Yep, we can do 3 times R times B. Okay? So there's our basic formula now. V equals 3 times R times B. Is R changing? Is V changing? All right. So we've got 3 variables in here. Okay? What does that mean? Do y'all understand why I say 3 variables? We've got V, we've got R, we've got B. Okay? So we've got 3 variables. This is one that's up at the higher end of the difficulty level from a project perspective, okay? Do we have a relationship between R and B? Do you think R and B are changing in a similar fashion? How are they changing? We could say R squared plus B squared equals this squared. Yeah? But what does that do? That adds another variable in there for us, doesn't it? So that relationship exists, but I don't think it necessarily helps us here. Can we find theta? Yes, but what does that do? Add another variable in there. Is there a relationship between R and B? And I'm going to redraw our cross-section of the pool, but just the triangle part, okay? Because this rectangle part up here doesn't really matter, does it? I'm going to redraw the triangle part. And we know this is 12. Now, trick question. What is that? 3, 4? I'm talking about for the whole pool, okay? It's 2. How did you figure out 2? 2's nowhere in the problem. Very good. Remember, we've got a rectangle sitting on top of this up here. And we know this rectangle is 1. So this part of the triangle must be 2 because the whole shooting match is 3. So we've got 2 and 12. And those are never going to change, right? Yes, sir.
I think R over 2 equals R over 2 equals B over 1.
Where does he get that from? Similar triangles, ratios of triangles. Do you see that the water is going to have to stay, the water level will have that triangle right here for the water level is going to stay in a similar format to the whole triangle there. So we'll have similar triangles. So R over 2 equals B over 12. Well, we need to, if we go back and think in our heads, kind of hard to think with anything but our heads, but if we go back and think, how do we probably need to solve that for R or B. Because if we can solve this for R, we can get just B's over here. If we can solve it for B, we can just get R's over there. What do we want over there in that formula, R's or B's? R. Why? We know what R is, right? The water level rising. We want to know what dr dt is. So that if we want R's over here, what do we need to solve this for? B. B in terms of R. Can you take this equation right here and solve it for B?
Yes.
Okay. Go for it. I would cross multiply and get 12R equals 2B, so B equals 6R. Okay? Okay, can we put R equals 1 in here now? If we put R equals 1 in here, we need to put R equals 1 in this one also, right? And if we put R equals 1 into both of them, do we have any variables left? And so when we take the derivative, what do we get? 0. So the pool's not filling up. We're pouring water in, but the water level's not rising? I don't think so. So what do we need to do now? We need to take this 6R and come up here and finish off the problem. So put 6R in. See if you can finish off the problem at this point in time. We will have V equals 18R squared. And you should be able to find a solution for R there. Miss Looney, I see frustration. How can I help you? Where did you get lost at? Do you understand this here? With the triangle, the green triangle? Do you understand why we can leave the rectangle off at the top? Because we're filling this pool up. So the water level is just up to this blue line here. Well, it doesn't really matter what's up there because the water level is not up to that point yet. Once we get the water level up to here, the problem changes, and we're not going to go there. That's above our program. So we're just going to forget about that. So then this green triangle is really the only part that we're worried about. So now, once we look at that, we know that it's 12 across the top because it's got to be 12. It's 2 because we were told that the whole length from this point here, from here to here, is 3. Well, on the short end, on the shallow end, it was 1. So that means that this rectangle right here is 1 on both sides. So that means this down here has to be 2. So this part of the pool is 2. This part of the pool is still 12. The water is going to have to be in the same ratio as they are. R over B equals 2 over 12. Think about putting water in here. If I pour water in here, what's going to happen? The whole water level is going to go up, which means that the R here is going to get a little bit higher, and the B here is going to get a little bit longer. But they're going to change in the same ratio all the time because as I'm pouring water in, it's just going to stay level in there. So the water level is going to continuously rise up at a slow pace based on how this is based there. Okay. Well, let's look at this. This is the pool. This is the water. We know this is 2. We know this is 12. This is going back to geometry. Do you see 2 similar triangles? Remember, similar triangles have the same size angles, but they differ in size. If we have similar triangles, then the side lengths are in proportion to one another. So R, the short side here, is in proportion to 2 as H is in proportion to 12. And we could have wrote that as 12 over H equals 2 over R if we wanted to. Small over large equals small over large. And then from that we can figure out what B is. And there seems to be quite a bit of discussion over here about what the dV dt is, or something over here, right? So let's see if we can finish this off. Well, if we take the derivative, what do we get for the derivative? 36R dr over dt. Well, that sounds right. Do we know dV dt? Okay, so we can say 1/4 equals 36. Now we can plug in for R. What do we put in for R? 1. So we're looking for dr over dt. So what are we going to be doing there? We need dr dt by itself, so we're going to do what? Divide by 36, which will get us that dr over dt equals 1 over 144 meters per minute. So it's going to rise at 144th of a meter every minute. Okay? Yes, ma'am? Water is being pumped in, and there is 1 meter of water. At what rate is the water level rising when there's 1 meter in there? We're putting those two things together. Yes, ma'am.
When we're saying R is 1, so it's like R is like where the 3 meters is?
Yes. Yes. This level here is rising at a rate of 1 over 144. That's how fast it's going up. Yes, sir.
We just don't care about 1 meter of water in a deep vein.
Yes, that's where we got, that's how we got that R equals 1. See, because we're concerned about this when there's 1 meter of water in the deep end. So that's how we know that R is 1 there, okay? If we had done this problem when R was 0.25, we'd get a much different answer. Does that make sense? Tell me about describe filling up this pool. When you first start, what's going to happen? It's going to go up very fast. Why? We're filling in a real small trough down there, okay? And the further up we go, we get to a point where we can barely even see that the water level is rising at all. Yes, sir?
This is only for the triangle part. What about the rectangle?
Very good. Why do we not need to worry about the rectangle right now? Because at 1 meter, where is the water? Is any water going into the rectangular part right now? No. So see, this formula works as up until R is 2. Now once we get higher than 2, then we've got a totally different problem. And we're not going to worry about that one today. Because once we get to there, it actually becomes an easier problem. Because think about it. Once we get up to 2, then is the triangle moving at all anymore? No. Is the H changing at all? I mean, yeah, the H is not changing anymore, is it? Because it's filling up the whole 12. This 6 isn't changing. All this changing is just the water level then. So it's actually an easier problem when we get up to the 2 there. Okay? Now, question for you. Does this formula hold true when the pool is bone dry and you start pouring water in? Why not? Now, okay, but I could put it when when I put the first drop of water in. This example here, this dV dt equals 36R dR dt describes the water level in this from once we get water in the pool all the way up to 2 feet. Why does it not describe it when we put the first drop of water in there? What's different when I'm putting the first drop of water in? R is 0, yeah, but something else. But what about when the second drop of water goes in? Describe it. Close your eyes. Tell me what this looks like. When I put the first drop of water in, tell me what's happening. Don't go to sleep with your eyes closed. Just it's not even rising. When I put those first drops of water in, the water level's not going to rise at all. Why not? It's got to disperse, right? Those first few drops of water. Go to an empty pool sometime and pour a cup of water in. See how much the water rises up. None. Why? Because what's got to happen first? I've got to fill up this 6 meters worth here. I haven't filled that up with those first few cups of water. So this works once we get water in the pool, once we get a thin layer of water down in the bottom of that trough, then this same pattern would be followed all the way up. But not with the first drop. We've got to have some in there to begin with. Okay? So, very, very intriguing problem here. Do we have some understanding of that? I am recording this so you can suffer through this again later if you so desire. All right, let's keep on moving to another problem here. That's another trough one. You can do the same way. Conical tanks we've dealt with. We may come back to construction here in a minute. We may come back to the boat here in a second. I want to go over here to one of the your turn problems. I don't want to do that one and scare you just yet. There we go, the shadow. Yes, sir. 24. What's different about 24?
Say 1 meter of water at these ends. It start pulling from the first fall. Now we don't have to do that one.
Okay, let's see. If water is being pumped into the trough at 2 cubic feet per minute, how fast is the water level rising with the depth H is 1 foot? And B part, the water level is rising at 3. You can do that one. Why do we not need to worry about the deep end and shallow end here? What's different about this picture and that picture? We don't have another piece out here. The shape is always a triangle there. Okay? I don't know if you're going to be able to do that one or not, but I want you to suffer through it on your own for a little bit, and we'll come back later and look at it, okay, if we need to. I do want to go look at the shadow one because the shadow normally scares people to death and blows their minds. So let's go look at the shadow. 33. All right? The shadow. And let me see if I can find a graphic of this because I think it works best when you can actually see this moving. I think I found one the other night. Read that problem, and it's rather simple. It's a rather simple problem algebraically, but it's very difficult to see sometimes. Why haven't you updated? Oh, because I haven't been in here forever. Come on, load up. Load up. There we go. Where is it? I think it's right there. Okay, what's going on in this? Describe what's happening in this picture, please. Okay, a man is walking away from the light pole. Okay? So this is what it's going to look like if it will pull up here. Load. There we go. Look at this. Do you see that his shadow, if you look up here at this graphic, do you agree his shadow is going to be getting longer the further away he walks from the pole there? Okay? So what we've got to do is we've got to determine, so that's a graphic of what the picture looks like. We may come back and look at it in a second. Let's see what we've got going on here. A man 6 feet tall walks at a rate of 5 feet per second, bless you, away from a light that is 15 feet above the ground. When he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? At what rate is the length of his shadow changing? Okay? Can you see some relationships here? Similar triangles. Okay? So we're going to be looking for some similar triangles here. Now, this 5 feet per second, isn't that how fast the shadow's moving? Why not? Oh, triangles don't work like that, okay? The man is 6 feet tall, and he's walking away at a rate of 5 feet per second. So something's changing at 5 feet per second. What? So he's changing height as he's walking? His position. Where on this picture up here is changing at 5 feet per second? Okay, from the lamp post to where? To him, right here. This distance is changing. What do we want to call that distance? X, Y, Z, Q, P, R? X, okay. So this distance is changing at a rate of 5 feet per second. Is X getting longer or shorter? Longer, okay. So it should be positive. Would everybody agree with that? Not the fact that he's walking to the right, but the fact that the distance from the pole is getting longer, okay? Now, what are we looking for? At what rate is the tip of his shadow moving? Okay? At what rate is the tip of his shadow moving? The tip of his shadow is right, and let's use a different color. The tip of his shadow is right there. Now, at what rate is the tip of his shadow moving? And I want you to look at B part 2. At what rate is the length of his shadow changing? What describes the length of his shadow up here? X is not his shadow. Where is his shadow? So his shadow is from here to here. Would you agree with that? So that's changing too. What letter do you want to call that? Y. So there is a dy over dt also? You want to call, so we could say y for something over here? That's what you're saying? Okay. All right, so let's do that. Do y'all understand why it's so important that you draw pictures and label your graphs here? Because I'm telling you, on the problem a while ago, if you just wrote down dr over dt is 1 over 144, I have absolutely no idea where you pulled that number out of the air at, other than you looked on Rhett's paper and just wrote it down. If you don't have any drawing out there for me, I have no idea what R is. So we're going to call this A. So dA dt is changing. Now here's my question. Is that dA dt the answer for A or B? B. At what rate is the length of his shadow moving? Shadow changing, I'm sorry. At what rate is the length of his shadow changing? Because A is the length of his shadow, so we want to know what dA dt is. Then what is A asking for? At what rate is the tip of his shadow moving?
So it's like how much, yeah.
The total length, the little point?
Just the end.
Just the end. Okay. So we want to know how fast, I need a different color and I don't have any. We want to know how fast the tip of his shadow is moving. We want to know how fast it's going that way. So what is it? Jerry says that we're talking about that whole distance there and how fast it is moving. What do you think?
It's how far the tip of his, how fast the tip of his shadow is moving away from his body. Isn't that what it's asking for?
It says it's how, at what rate is the tip of his shadow moving. It doesn't say moving from his body. I think it's relative to the lamppost. So I think Jerry is right. I think we're looking for, we've got another variable here. What do we want to call our purple line? D. Okay. So now we got a DD and DT, don't we? So we're looking for this, we're looking for DD over DT, and that's going to be the answer for A part. dA over DT is going to be the answer for B part. Now, do we have any relationships between any of this stuff? Probably. Okay. Well, very good. We know X plus A equals D. Would you agree with that? X is this blue line, A is the red line, and the blue plus the red. Remember, D is out to the tip. So then dx plus dA equals dd. Would you agree with that? And we already know what dx is. All right. Now, but we don't know what dA or dd is. That's what we're looking for. Do we have any other relationships? Lauren said we had similar triangles. What similar triangles do you see up here in our picture? You mean, can you tell us something? We have a big triangle. Let's pick a yellow here. We have a big triangle from here to here to here. And the small triangle is what, you mean? We'll have a small triangle. I can't use that. Here, let's pick out a totally new color here. Green's not going to show up good on the green. Yeah, that's not pretty, is it? All right. Do you see that we've got the yellow triangle and the almost black triangle there to look like? So, we've got some proportion thingies here. What do we know about the height of the yellow triangle? It's 15. Is it changing? So it's always 15. It's okay to put that down. What do we know about the height of the other little black triangle here? 6. Is it changing? Not unless he has a growth spurt, and we're going to assume he's not growing anymore, okay? 15 is to 6 because that's the height of each. Now, how long is the big triangle? D. How long is the little triangle? A. Well, that didn't help us any, did it? Or did it? If we cross multiply these, we get 15A equals 6D. Do we want to solve for A or D? All right, so we get 15A over 6 equals D. All right, A equals 6D over 15. I'm just doing what y'all tell me to do, right? I don't know that it does matter.
Because plugging back into the regular formula, you're going to have to find the other one later.
We're going to have to find either one. There's not a wrong way to do it, and there's not a right way. I mean, there's not one wrong way. There's not one right way, okay? Either of those will work. But now, look at where we're at. We got over here in our purple to this point right here. We got dx's, da's, and dd's. And now we've got a equals 6d over 15. So what are we going to do now? Find the derivative of which one of these do you want to use, A or D, Sutton?
Let's do A.
So dA over dt equals what?
2.5. Or, excuse me, 2 over 5, which is equal to 6 over 15.
Yeah, let's go with the 2/5. That's much. 2/5, almost.
Oh, D, yeah.
Well, how does that help us, people?
We have the formulas up there.
So now we can take this thing and go back up here, and in place of dA, we can put 2/5 dd, can't we? So dA over dt equals 2/5 dd over dt. So now we're comfortable plugging some stuff in? What can we put for dx over dt? 5 plus 2/5 dd over dt equals dd over dt, right? Well, what can we do now? We've only got one variable, so it should be solvable. What thing? Okay, how are we going to solve it there? We're going to subtract 2/5 dd dt from both sides. How do I subtract 2/5 dd dt from dd dt? That's 1 minus 2/5, which is? So we have 5 equals 3/5 dd over dt. So then what's dd over dt? 25 over 3. What are my units? Feet per second. Feet per second. Now, 25 over 3 feet per second is dd. What is that the answer for, A or B? A. That's how fast his shadow is moving. His shadow is moving at a rate of 25 over 3 feet per second, a little over 8 feet per second. How are you going to find B? Look at this right here. We've got dx, we've got dd, we can find dA, can't we? Very good. So if we do that, we've got 25 over 3. So dx plus dA equals dd is what we said. We know that's 5. We're looking for him. And we know this is 25/3. So dA, write it right, Ely. dA over dt equals 25 over 3 minus 15 over 3, which is 10 over 3. So his shadow is getting longer at a little over 3 feet per second, if I did that right. Do you understand why that blows people's minds? All right, I have an intriguing question for you. Turn the man around, walk him towards it. Does that change anything? Josh says, just throw a negative in at the end. It's got to be right there. Well, let's go back up here. What would change in this green line right here? What would change in this green line? 5 would become negative, which would mean that we would have a negative 25 over 3, right? So would it change anything? No, it just means that this shadow is moving at a negative rate. It's getting shorter. Would it change anything down here to have a negative 25 over 3 and a negative 15 over 3? Because this would be negative, right? But wait. Understand something. Mathematically, y'all just told me this would be negative, right? So then this would be negative, right? So then it's not 10 anymore. At least not in my algebra world it's not. What is it? It's negative 40 now, isn't it? So then dA over dt, his shadow is getting shorter faster because he's walking the other direction?
Yeah, that makes sense. Yeah, I like that.
He's getting shorter faster? Just by turning around, you made the shadow get shorter faster.
Think about like the sun. Like towards the end of the day, the shadow is really long, really fast.
Okay.
And then it knew.
Okay. So, but I just want you to look at, do you understand why the sign, S-I-G-N, of that 5 is very important to determine at the very beginning? Because it dramatically changes. You can't just stick a negative sign in at the end. Not if you want to get the right answer. Okay. Look, 34 is the same, is what we just did. 34 is what we just did, but it's moving towards the light. And it's 20 feet. So it's going to work the same type way here, okay? All right. I am not going to work any more problems for you, okay? My suggestion to you is to work through these and ask me questions. I'll be happy to answer questions. Oh, did electricity excite you there? Okay. Did electricity excite you? Da-dum-pump. Okay. I'm just on top of it this year. Woo! All right. Okay. I'll be happy to help you, but you need to suffer a little bit on your own. You need to struggle a little bit on your own to find out what your areas of weakness are. So this next hour that we have together is an opportunity I strongly recommend you work through the rest of these problems on 25 and ask me questions about them. Strongly recommend that, okay? If you'll ask those questions, then I can answer them. I can probably even find a key somewhere that I can give you to look over those things. I think so, because this will give you a much more comfortable feeling going into WebAssign. But it's entirely up to you, okay? So we will be spending no more class time discussing anything on related rates necessarily, okay? Probably no more class time. You've got next period to work on related rates, either 25, either the 25 or the WebAssign. You can decide who's going to work with you on your project. If you choose to work with someone, y'all can think some about your project. Tomorrow we're probably going to go back to doing some other application type stuff with it that's much easier to deal with than this here. This is the hardest part of it for another couple of weeks here. So, thank you very much. It's been a pleasure. About May 10th, May